Welcome to the session on tensor networks and neural network quantum states. Today, we are going to focus on two different variational quantum many-body formalisms to solve general interacting many-body Hamiltonians. And in particular, first, we are going to focus on how we can understand the degree of quantum entanglement in different quantum many-body Hamiltonians, and how we can use this limited entanglement to actually use two new variational methods to solve general interacting models. In particular, we will start with tensor networks and matrix product states, which are a variational method that exploits the finite amount of entanglement entropy that one-dimensional models have. And then afterwards, we will move on to a more sophisticated methodology called neural network quantum states that allow to solve systems that have a higher degree of quantum entanglement. To understand why we need variational quantum many-body algorithms, it is good to make a step back and look at our generic interacting fermionic Hamiltonian. So in particular, we usually have a term that has kinetic energy, that is Tij c dagger I Cij. This is the free Hamiltonian term that we can solve exactly. And then the term that it's usually hard to solve is the interacting term that it's Vijkl c dagger I Cj c dagger Kcl. In many instances, we can try to solve this interacting term by performing a mean field ansatz. And this gives rise to different quantum materials, including magnets, superconductors, charge density wave states, and many others. And when we do the mean field ansatz, we essentially transform this interacting term onto an effective single particle term, a single particle term that may break specific symmetries such as time reversal symmetry or gauge symmetry or spin rotational symmetry. And this has been the methodology that allowed us to study both magnets, superconductors, charge density waves, and so forth. Today, we are going to focus on the regime where mean field cannot be used. We are going to focus on the regime in which interactions are so strong that one cannot find an effective mean field Hamiltonian that describes the ground state of the system. And this regime is, for example, the regime where we have quantum spin liquid physics, or the regime where we have fractional Chern insulators. And of course, if we want to find an accurate estimate of the phase diagram of an interacting model. And the methods that we are going to focus on today allow us to tackle precisely this regime, the regime where we don't have an effective mean field Hamiltonian, and the regime that requires an exact numerical solution. And this is what we usually call strongly correlated quantum matter. The first point to raise in this direction is just to remember that we actually found two different types of interacting Hamiltonians in the previous sessions. We had interacting Hamiltonians that were fermionic Hamiltonians, in particular, where the interaction was effectively this type of, for example, density-density interaction, or you can think that it's also spin-spin interaction, the term that goes with Vijkl. But in other cases, we also had many-body Hamiltonians that were associated not to fermionic degrees of freedom, but actually to spin degrees of freedom. And these are the many-body Hamiltonians that appeared, for example, when we were considering quantum spin liquid physics. And these Hamiltonians were, for example, the Heisenberg model, that if you have antiferromagnetic interactions, is a purely quantum many-body model. So the first point to keep in mind is that actually these two types of Hamiltonians are equivalent from a mathematical point of view, meaning that we can actually make a specific mapping between spin Hamiltonians and fermionic Hamiltonians. This mapping is actually relatively complex, but we can actually understand it in a relatively simple way. So let us focus on a spinless fermionic Hamiltonian first. And let us focus first on a single site, just to understand how we can map the local Hilbert spaces between the two Hamiltonians. We have a fermionic Hamiltonian. A local Hilbert space essentially has two states. It has the empty state and it has the full state. So we have no fermion whatsoever and just one fermion. And remember, this is a spinless fermionic Hamiltonian, so we don't have spin degree of freedom. If you now think about a spin model, and in particular spin model with a single site, then our local Hilbert space also has two states, has the down state and has the up state. And now you can start asking yourself, well, how are the operators, let's say, moving one state to the other state? So in the case of the fermionic model, you could go from the empty state to the full state by applying the creation operator, C dagger. And in the case of spin, you could go from the down state to the up state by applying the ladder operator, in particular S plus. So in a way, one could try to identify the creation operator in the fermionic model with the spin ladder operator. So the operator that increases the spin by 1 in the spin model. And by the same argument, you could essentially identify the annihilation operator in the fermionic model with the ladder operator that increases the spin by 1 in the spin model. However, there's one thing that one needs to remember, that it's actually very, very important, which is related with the actual quantum statistics of the two models. So fermionic many-body wave functions are antisymmetric, whereas spin many-body wave functions are symmetric because they are bosonic. So when you try to use this very same argument, but with two sides or several sides, you actually see that this simple mapping between creation and ladder operator and annihilation ladder operator does not hold anymore, because you need to accommodate this extra sign that fermions have with respect to spins. However, one can just redefine this ansatz so that the sign actually corresponds in the correct way between fermionic and spin models. And this redefinition of the sign is actually what is known as the Jordan-Wigner transformation. So the basic idea is that you say that your spin operators, in particular the ladder operator that increases the spin, is the creation operator times some very specific phase that depends on the occupation number of the previous site. For the other ladder operator, you say that it is the annihilation operator times this phase, and then for the SC operator, essentially the number operator of the fermion minus 1/2. If you write this very specific mapping between the spinless fermionic operators and the S equal to 1/2 spin operator, what you actually find is that the algebraic relations between fermions and between spins hold. And in particular, you actually have an exact mapping between the Hilbert spaces between spins and fermions. And the way this is usually described is by saying that spin is effectively a fermion times string, meaning that the spin corresponds to the spin operator, the fermion corresponds to the creation and annihilation operators, and the string corresponds to this additional extra sign that we incorporated through the exponential in order to account for the commutation and anti-commutation relations of spin and fermionic operators. What this is telling us is that actually we can think that all interacting Hamiltonians are spin Hamiltonians, or that we can actually map interacting fermionic Hamiltonians to interacting spin Hamiltonians. And for the rest of the session today, we are going to essentially assume that we are always in the spin representation. And the reason for this is that in the spin representation, the wave functions are actually symmetric. And for the methodologies that we are going to focus on today, it is actually very beneficial to have symmetric wave functions. Okay, so now the idea is that we are going to take our general spin Hamiltonian that may have, let's say, non-local interactions due to the string operators, and we are going to ask ourselves, what do we have to do to solve the Hamiltonian? And perhaps what is most important, why solving the ground state wave function for a generic many-body Hamiltonian is so challenging? Well, the most important point is that if you want to solve the many-body Hamiltonian, the first thing that you need is to be able to store the many-body wave function. The second step would be to be able to find the many-body wave function, but perhaps the most important step is to actually store it. And the most important point to remember from today is that the actual challenge in many-body Hamiltonians is to store the wave function. We actually don't have enough memory resources to store the many-body wave function. And the two methodologies that we are going to focus on today, tensor networks and neural network quantum states, essentially tackle this challenge. So the basic idea is that you can think that in a typical quantum many-body Hamiltonian, you have an exact many-body wave function that is like this picture here on the left, and tensor networks and neural network quantum states actually allow us to store an approximate version of this wave function. It allows us to store something that it's not exactly the actual real wave function, but something that resembles the actual wave function, and that in practice allows us to compute all the observables that we would need with relatively high accuracy. Okay, and now let us go a little bit more into detail of why quantum many-body Hamiltonians are so challenging in general. So let us start with the simplest quantum many-body Hamiltonian, which is just a Heisenberg dimer. So we have two sites, site number 0 and site number 1, and we have an antiformal decoupling between them that here we take as 1. If you take that these operators are quantum mechanical operators that follow the typical commutation relations of angular momenta, what you actually obtain is that the ground state is a combination between the up-down state and the down-up state. And this is what we call a singlet state. It's a state that does not break traversal symmetry. It's a state where the expectation value of every single spin operator in every single site is actually 0. And what is most important is a state that it's maximally entangled. And the question to understand quantum many-body wave functions boils down to thinking, how does this type of wave function generalize when you have a macroscopic system, when you have a system that has many, many sites? So let us go in this direction. So now let's think that we start first with two sites, and with two sites you effectively have a Hilbert space with 4 states. So you have the state that is up up, the state that is up down, down up, and down down. So effectively your Hamiltonian is a 4x4 matrix, and to find the ground state energy and the ground state wave function, you just need to diagonalize this 4x4 matrix. And when you do that with this Hamiltonian, you essentially obtain the singlet ground state that we showed before. If you start now adding an additional site, so now you consider that you have 3 sites, then your Hilbert space actually increases. You have the up, 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 down, and so forth. So instead of having 4 states, now you have 8 states. Just by adding an additional site to your model, the number of states became twice what it was before. And of course, you can keep doing this, right? So now you can think about adding an additional site so that in total you have 4 sites in your quantum many-body Hamiltonian. And then when you do this, you essentially get that the number of states that your Hilbert space has is 16. So now twice of what you had with 3 sites. And you can now imagine that this is going to very, very quickly increase the dimension of the local Hilbert space. And in particular, every time that you add an additional site, then the dimension of the Hilbert space becomes twice as large. What this actually means is that the dimension of the matrix that you need to solve in a quantum many-body Hamiltonian, in particular in this spin 1/2 Heisenberg model, increases exponentially with the number of sites, and in particular increases with 2 to the L. And this increase in the dimension of the matrix that you need to solve is essentially what makes quantum many-body Hamiltonian so hard to solve. Even if you think that you don't need to generate, or that you don't need to store the whole matrix at once, but you could generate every single element, just if you think about storing the wave function, this would mean that you would need to store 2 to the L coefficients in a many-body wave function. And of course, this is the most challenging part, and you may very easily run out of resources to store all these coefficients. So the way that we usually think about this is that we have our Hamiltonian, we may have some very specific algorithm to get to the many-body ground state wave function, and this ground state wave function is written in some very specific basis. And maybe the simplest basis for a spin Hamiltonian is the basis of up and down states. So you now can think that this S1, S2, SL are up, down, up, down, up, down with all the possible combinations. So in practice, to know your ground state wave function, you just need to know all these coefficients over here, which is, of course, 2 to the L coefficients. So the actual trick to deal with these many-body wave functions is to come up with some way of storing all these coefficients, or at least storing a good approximation to these coefficients. And this is what tensor networks and neural network states do. Okay, so let us start with matrix product states, which are a very specific type of tensor networks, and it's the type of tensor network that we will focus on today. So we have our quantum many-body Hamiltonian that has, let's say, L sites, L spins, and our objective is to actually find some way of storing all these coefficients that form the quantum many-body wave functions. So the coefficients C, S1, S2, SL. Of course, if L is a large number, let's say on the order of, let's say 30, 40, then we cannot store all these coefficients. But what we can do is to sort of find some parameterization of these coefficients, meaning that we have 2 to the L coefficients, and we could argue that perhaps these coefficients can be represented as a product of matrices M1, M2, ML, and there are as many matrices as the local dimension, which means 2. So we have one matrix force being up inside 1 and one matrix force being down inside 1, and the same for every single side. So in practice, if we use this parameterization, we would need to store a number of coefficients that is proportional to L, with L the number of spin sides, and M squared. And M is essentially the dimension of these matrices that we just decided to define. This is, of course, a choice that we make. This may be a good choice to parameterize all these coefficients, or this may be not a good choice to parameterize these coefficients. So now the first question is, how do we know that this is a good choice? And the second question, well, what is the reason why this is actually a fitting choice for a many-body wave function? It turns out that that is actually an excellent choice, especially for one-dimensional systems. And for two-dimensional systems, it is one of the best methods that we have so far. And in particular, that is what it's called the matrix product state ansatz. Choosing to define the coefficients of the wave function in that way is essentially what gives rise to the matrix product state formalism. And in particular, this formalism has been the most successful method to solve some of the most paradigmatic quantum many-body models that we have in quantum materials. And in particular, if you think about the two-dimensional apart model, including doping and including second neighbor hopping that essentially gives rise to unconventional superconductivity, has been solved with tensor networks. And the most accurate results are performed with matrix product states. And the other type of paradigmatic quantum many-body model is the two-dimensional frustrated spin models, and in particular two-dimensional Heisenberg model, both in the triangular and Kagome lattice. And the most accurate results for these models, the results that show that we actually have quantum spin liquid physics, even when we deal with the exact solution, are also being done with matrix product states. So today we are going to see, let's say, why these matrix product states work well, and how do we have to do in order to find the ground state with this methodology. And to understand why they work well, we first need to understand how the entanglement of a many-body wave function is. Meaning, when we have a quantum many-body Hamiltonian, we expect that the ground state is not going to be a product state, it's not going to be a classical state, but we may also expect that perhaps the entanglement is not as large as it could be. And this is actually the key reason why matrix product states and neural network quantum states work actually very well for ground state properties. Okay, so let us start with a typical quantum many-body model. Let us just say that we take the whole system and we divide it into two. So we say that we have a part of the subsystem that we call A and another part of the subsystem that we call B. In general, the quantum many-body wave function is going to be, let's say, a mixture between, let's say, many different components. But what is important for us is to define a quantity that allows us to know how entangled the many-body wave function is. And in particular, it is useful to first consider what a not entangled wave function is. So if you have a quantum many-body system whose wave function is essentially just a tensor product between wave function inside I or wave function in subsystem A and wave function in subsystem B, then this type of wave function is not entangled. This is just the most trivial state that you can have in this system. And typical examples of this type of wave functions, for example, for two sides, are shown here. So the state up-down by itself is a state that it's not entangled. It's just a tensor product between up state on A and down state in B. And this wave function here that has a linear combination of up and down and another linear combination of up and down, but now inside 2 is also not entangled. So you can think that this is just the spin in the x direction inside 1, this spin in the x direction inside 2, and then you just have a tensor product between those two. Those are states that are not entangled. So now the question is, well, what is a state that it's entangled? Well, a state that it's entangled is actually the singlet state. The ground state of the Heisenberg model for two sides is a state that cannot be written as a tensor product of a state inside A and state inside B. So now the practical important question is to know, well, why is this state entangled and how can we measure how entangled a state is? And in order to do this, we are going to define something that is called the entanglement entropy. That it's a very simple measure to know how entangled a state is. So the actual trick is just to take, let's say, the many-body wave function of your quantum many-body system that here we call psi, to define the full density matrix of the many-body system. And now, once you have the density matrix of the full many-body system, you trace over the degrees of freedom in subsystem B. When you do this, you essentially obtain the density matrix for subsystem A. And with this density matrix for subsystem A, you can essentially define an entropy associated to it. And the way you define the entropy is, well, in the same way as we do in statistical physics and thermodynamics, just by defining the trace of density times the logarithm of the density. And what is important is that this entropy is 0 for a state that it's a product state, namely for a state that it's a tensor product between a state inside A or in subsystem A and state in subsystem B. And for some states, it's going to be non-zero. So in particular, if you compute the entanglement entropy for the singlet state that we showed before, you are going to see that the entanglement entropy is logarithm of 2. So this quantity, the entanglement entropy, allows us to know how entangled a state is. And it is actually a key point to understand why matrix product states are a very good, let's say, ansatz. And to understand this point, let us look at a relatively simple one-dimensional quantum many-body model. And it is simple because we can actually solve it analytically. So you can think that you take a one-dimensional chain, and you take spins in your chain, but now you put a Heisenberg coupling only between pairs of sides. So you do it between side 0 and side 1, side 2 and side 3, side 4 and side 5, and so forth. But you don't couple these sides between each other. This Hamiltonian is actually very easy to solve because you can think that the ground state wave function is going to be a tensor product of all the ground state wave functions in the different sites. And in particular, you can think that the total ground state of the system is going to be just a singlet state in each bond tensor product, all the different pairs that you have in the system. This can be a relatively, let's say, simple Hamiltonian, but the key point is that you can think that this is the minimal model for a quantum spin liquid that has a very large gap. So this system, of course, is not gapless. The system has a very large gap that is the energy difference between the singlet and the triplet state. And you can think that all the arguments about entanglement entropy can use this sort of Hamiltonian as a model Hamiltonian in order to predict how it looks like. So now the question for us is, what is the entanglement entropy of this Hamiltonian? And of course, when you compute the entanglement entropy, you always need to decide what is the size of your subsystem. So if you now think that you have an infinite one-dimensional chain with this type of dimerization, you could make two and many more different choices for the bipartition of the system. So you could say that, well, I'm going to take a subsystem A that just includes these two dimers over here, or I could take a bipartition B that contains all these different dimers over there. So now with these two bipartitions, you could take the manifold state wave function that we have in the previous slide, and you can compute the reduced density matrix by tracing over the part of the system that you are not considering. And the key point is that for this many-body state wave function, all the sites whose singlet states are contained inside the partition are not going to contribute to the entanglement entropy, because they are going to have essentially zero entanglement entropy because the whole singlet is inside the partition. And the only states that actually contribute to the entanglement entropy are those that are being cut by the bipartition. And in particular here, you are going to see that these two states contribute to entanglement entropy, and these other two states also contribute to entanglement entropy. And for this other bipartition, only this bond over here and this bond over there contribute to the entanglement entropy. What it's important to note is that the contributions for the first bipartition are actually the same as the contributions for the second bipartition. So the entanglement entropy of this system actually does not depend on the size of the bipartition. In particular, you can think that in both cases, if you consider the Hamiltonian before, the entanglement entropy is going to be 2 times the logarithm of 2. Okay, now let us try to play this very same game, but with a 2-dimensional system. And we are going to define a 2-dimensional Heisenberg model in a very similar spirit. So now instead of having dimers, we are going to consider clusters of 4 sites that are coupled. And what is important is that if we couple, let's say, these 4 sites, we can write down a ground state wave function that is essentially a tensor product between the ground state wave functions of all the different tetramers in a tensor product way. Now, with this ground state wave function, we can again take 2 different bipartitions of our system, and we can ask ourselves what is going to be the entanglement entropy for the 2 bipartitions. So we can take bipartition number A that cuts essentially all these bonds over here, so a total of 8 bonds, or we can take bipartition B that cuts many, many more bonds. Now, if you compute the entanglement entropy, you will see that the entanglement entropy is essentially proportional to the number of singlets that you are cutting. And in particular, for this bipartition, for bipartition A, you are cutting much less singlets than for bipartition B. What this actually implies is that the entanglement entropy for bipartition B is going to be much bigger than for bipartition A. And you can actually show that the number of bonds that you cut, which is effectively a number of singlets, is proportional to the length of the boundary of your bipartition, which we denote in this way. So in a 2-dimensional system, the entanglement entropy actually grows with the size of a partition, whereas in a 1-dimensional system, it didn't. And this is actually a key point to understand why 1-dimensional quantum many-body models are completely different from 2-dimensional quantum many-body models. And in particular, this is what it's called the area law, which essentially states that if you have a gapped system, both in 1 dimension and 2 dimensions, or in higher dimensions, the entanglement entropy of the ground state just depends on the length of the area that separates your subsystem from the rest of the system. In a 1-dimensional system, that area that separates the subsystem from the rest of the system are actually just 2 points, or this bond over here and this bond over there. And that's why the entanglement entropy didn't grow. Whereas in a 2-dimensional system, then the boundary actually grows with the size of your subsystem. The key point is that matrix product states essentially parameterize states that have a certain bound on the entanglement entropy. And this bound on the entanglement entropy is actually set by the dimension of these matrices, meaning that if you take a small dimension, you parameterize the states that have a low entanglement entropy. If you take a very large dimension, you parameterize the states that have a very large entanglement entropy. So what this is actually telling us is that this type of parameterization is going to be very efficient for one-dimensional models. For two-dimensional models, we may need to take a relatively large dimension of the matrices, but it may still work. And this is essentially the idea of this many-body parameterization. So you can think that the whole Hilbert space is this green circle over here. These are all the potential states that you have in a many-body Hamiltonian with L sides that have 2 to the L degrees of freedom. A matrix product state, of course, does not parameterize all the possible states. It's only going to parameterize a very teeny tiny portion of this Hilbert space. But what is important is that this portion of the Hilbert space is the portion of states that follow area law, entanglement, and in particular, the entanglement of those states grows with the logarithm of the dimension of the matrices that you use in your matrix product state ansatz. This ansatz, the matrix product state, is essentially enforces a maximum amount of entanglement in all the states that you consider, amount of entanglement that grows logarithmically with the one dimension. And for one-dimensional systems, that is actually perfect because one-dimensional systems, as we saw before, have entanglement entropy that does not grow with the system size. And even though originally this type of variational algorithm was developed for ground state properties, we can actually use also matrix product states to compute up to a certain degree time evolution or excited states or open systems in one-dimensional systems, and sometimes even in two-dimensional systems, even though, of course, it becomes much more expensive. Of course, matrix product states do not work in every single scenario, and the scenarios in which they actually break down are very much related with the amount of entanglement that the states involved have. So in particular, if you have a system that has an entanglement entropy that is very large, then it is not going to be well captured with a matrix product state. And this, of course, holds in cases where you consider, let's say, high-dimensional systems, or even if you consider one-dimensional systems and you do time evolution to very long times, because when you do time evolution, the entanglement entropy actually grows linearly with time, or, of course, higher dimensional systems, or even if you think about highly excited states where the area law no longer holds, and of course, if you are in far from equilibrium, because the area law applies to the ground state. The interesting thing about the matrix product states is that by just changing the size of your matrices, you can parameterize a bigger or smaller portion of your Hilbert space. So if you take a small one dimension, you parameterize a very small part of your Hilbert space. If you take a bigger one dimension, you parameterize a bigger part, a bigger one dimension, an even bigger part, and so forth. And eventually, if you take a one dimension that is large enough, you can parameterize the whole Hilbert space. Of course, this is not the limit that it's interesting for practical purposes, because in those cases, we would have an exponentially large number of parameters. But what is important is that matrix product states allow you to interpolate all the way from simple product states to fully entangled states that cover the whole many-body Hilbert space. Something that is very convenient for matrix product states is that actually there's a very simple graphical representation of the state itself and even of algorithms themselves. And the idea is that we can think that we can represent graphically the different elements of a matrix product state algorithm. So you can think that a scalar is just a single point. A vector is a point that has a dangling bond. A matrix is a point that has two dangling bonds that would correspond to the two indexes of a matrix. And a rank 3 tensor would be a point with three dangling bonds, where each bond is each one of the indexes of the rank 3 tensor. And many of the tensor product algorithms and matrix product state algorithms can be represented very nicely using this type of nomenclature. So for example, you can think that a matrix product state is essentially a diagram that is represented by all these points, and each one of these points is one of the matrices of our matrix product state. And then we have a dangling bond, S1, S2, S3, that is essentially this dangling bond over here. And then we have different bonds that couple the different matrices that are essentially the internal indexes of the matrices that are summed over to compute the coefficient. So if you want to represent a single matrix product state, then you can just write this very specific diagram. And now if you want to represent a matrix product operator, that would be essentially the Hamiltonian or any operator acting on the matrix product state, then you can write it in this way. You have indexes, sigma 1, sigma 2, sigma 3, and so forth, that essentially represent one of the indexes of your operator or of your matrix. Then you have the other set of dangling bonds that represent the other index of your operator. And now you have rank 3 or rank 4 tensors that are essentially the matrix product operator representation of your Hamiltonian or any other operator that you are considering. And if you want to, for example, apply a matrix product operator to a matrix product state, what you can actually do is just to link the two diagrams. You take the operator that you want to apply, you take the matrix product state that you want to apply, and now you transform this type of, let's say, diagram onto something that looks like a matrix product state. And the trick is that to make this transformation, the only thing that one needs to do is to do products between every single matrix that you have over here. So you essentially sum over this index. And the actual trick is that, in principle, this would, of course, give rise to a bigger matrix. But if you do a singular value decomposition and retain only the most important part of your tensor, then you can keep a certain you don't have to increase the amount of computational resources to store this result. Okay, so with this, we can represent matrix product states and matrix product operators. Of course, when we deal with a Hamiltonian, one of the most important points is to actually find the ground state. So an important question, how are we going to find a ground state using this matrix product state representation? And so the idea is actually relatively simple. You can think that this matrix product state representation is just a variational wave function. And when you have a variational wave function, you can find your ground state just by minimizing over all the parameters of your variational wave function. So in particular, we essentially define the energy of the matrix product state, that is the expectation value of wave function, Hamiltonian wave function over the norm of the wave function. And of course, this can be written in a more, let's say, useful way by using Lagrange multipliers. So we want to minimize this expectation value with the Lagrange multiplier that puts the constraint on the norm of the wave function. And now what we have to do is just to minimize with respect to all the parameters of psi. And in particular, for a matrix product state, the parameters are the matrices themselves. So from a variational point of view, you can think that finding the ground state with a matrix product state is essentially minimizing the energy with respect to the different matrices that you have in your tensor network. And you can actually represent this diagrammatically in a very simple way, just using the diagrams from before. So you just have to remember that every single tensor in a matrix product state is actually multiplying each other. So performing the derivative is essentially just removing from the diagram whichever tensor you are deriving with respect to. So from a diagrammatic point of view, this equation, that is the variational principle, essentially gets translated onto this type of diagram with tensor networks. And all the idea is that you can think that this is just an eigenvalue problem. So you can think that here you have 3 different indexes, and here you have 2 different indexes. So you can think that you just need to find what are the eigenvalues and eigenvectors of this problem. And now what you can do is you perform the derivative with respect to this side. Let's say find the eigenvalues and eigenvectors that minimize this equation, update this side, then perform the derivative with respect to another node, and another one, and another one, and another one, and so forth. And this iterative algorithm that essentially minimizes first one matrix, then another matrix, then another matrix, and so forth, is what it's called the density matrix renormalization group algorithm. What is important is that this is an extremely efficient algorithm for one-dimensional models. And the most important point is that to optimize this variational many-body wave function, you only need to optimize one matrix at a time, which from a computational point of view is a very important point. Okay, so this was about matrix product states, but of course, this idea of tensor networks can be extended to many other architectures. So one can consider, of course, let's say the one-dimensional chains of tensors that we addressed before, which is the matrix product state, but you can also think about, let's say, two-dimensional networks, or even, let's say, more complex networks. These types of networks are in general called tensor networks, and some of them are easier to optimize than others. In particular, matrix product states are the tensor networks that are the easiest to optimize, and there are some very specific tensor networks that can be also optimized. Now, the idea is that there are different tensor networks that can be especially useful in specific cases. And in particular, let me emphasize two of them. One is the multiscalar renormalization ansatz that is especially interesting for systems at criticality. So when we are right at a critical point between two different phases. And the reason is that these types of tensor networks actually allow to have much more entanglement than matrix product states. And something that is very interesting is that they can actually allow to deal with, let's say, strongly correlated systems that are described by conformal field theories. Then the other type of tensor network is called a projected entangled pair states. So this is effectively a two-dimensional extension of matrix product states. So instead of considering tensors that are coupled in a line, you consider them coupled in a lattice. And this is a very interesting architecture for interacting two-dimensional quantum many-body models. In comparison with matrix product states, they are harder to optimize. So there's not an algorithm as simple as the density matrix renormalization group to optimize them, but nevertheless, they are very promising for two-dimensional models. Okay, that is everything that I wanted to tell you about tensor networks. Now, let us move on to a different type of variational many-body wave function, which are neural network quantum states. Neural network quantum states actually don't originate from physics. They come from an inspiration from machine learning. And you can think that in machine learning, there are, of course, many tasks that one is interested in doing. You have, let's say, supervised learning that essentially allows you to say if, let's say, the picture, a certain picture is a cat of a dog. So this is the typical classification problem. You can also have generative learning that essentially allows you to, let's say, model probabilities. And in particular, there are all these, let's say, very impressive demonstration with large language models and transformers. And you also have other types of machine learning methods like reinforcement learning that are essentially based on reward-based decisions. What is important is that in machine learning, we many times have, let's say, a computational method that is common to many of these cases, which are called neural networks. And neural networks are just a family of parametric functions. Neural network is just a convenient way of defining a function that goes from an n-dimensional space to an m-dimensional space. And the different dimensions of the input and the output depend on the very specific problem. So the idea is that this generic wave function essentially has 3 parameters, and one optimizes these parameters for a very specific purpose. And the way these parameters are optimized is by defining something that is called a loss function, that is essentially the difference between the real output that you have and the real output that you have gotten when you put a very specific input. And the typical loss is, for example, just the difference to the second power. Of course, this loss depends on the problem that you are dealing with. And if you think about a classification problem, you can think that the loss is saying if it is a cat or a dog. So the difference between predicting that it's a cat or predicting that it's a dog with respect to the actual value. And if you are doing some other problem machine learning, then the loss is going to be different. The dimensions of your inputs are going to be different. The dimensions of your outputs are going to be different. What is important is that this is actually not so different from what we need for quantum many-body systems. So you can think that in general, deep neural networks map a very specific input X to a very specific output Y. And they have a set of parameters inside the wave function. So in a mathematical form, you essentially say that the neural network is a function that depends on the parameters lambda and the input X and give rise to an input Y. And now the idea is that you can actually think that this type of ansatz may allow you to parameterize a many-body wave function. That is essentially the idea of neural network quantum states. So you can actually think that there's a whole hierarchy of, let's say, variational quantum many-body algorithms. You can think that mean field for a spin model, for example, is the simplest type of variational algorithm. You minimize the energy over the set of product states, meaning states that have no entanglement whatsoever. Then the next level that you could do is matrix product states that essentially allows you to minimize over the set of states that have a finite amount of entanglement given by the bond dimension. And neural network quantum states essentially allow you to make the next step, to minimize over states that are parameterized by a neural network. And the idea is that neural networks actually allow you to make generalizations of matrix product states and tensor networks, and what is most important, to actually leverage many of the developments that have happened in machine learning to actually solve quantum many-body Hamiltonians. So from the point of view of, let's say, the whole map of actual states, you can think that, say, neural networks are falling in this category. So you have first the whole set of many-body quantum states that have as much entanglement as you want, and that whose dimension scales exponentially with the system size. Then states that are parameterized with tensor networks and matrix product states, for example, are gapped one-dimensional models, and then there may be some other models that are not gapped, but they are also well captured by MPS. Then you can think that some other types of tensor networks, such as projected and entangled pair states, allow you to parameterize an even bigger set of many-body states, and neural network quantum states actually include all those states. And in particular, there are specific mappings of neural network quantum states to matrix product states. So a subset of neural network quantum states actually allows you to parameterize all the matrix product states. So matrix product states are actually contained within neural network quantum states. Okay, so the idea is relatively simple. We take again our quantum many-body Hamiltonian, that is our Heisenberg model with spin 1/2. We want to parameterize the quantum many-body wave function that has all these coefficients, in particular 2 to the L coefficients that we cannot store in memory in general. So before, we were essentially generating all these coefficients with a tensor network, and in particular with a matrix product state. And now what we do is we will generate them using a neural network. And the idea is relatively simple. You can think that from the point of view of a neural network, the problem that you want to solve is to find a function that allows you to map a very specific spin configuration onto the coefficient that it has in the ground state. So the input of your neural network is, for example, up, up, down, so forth. So the very specific state from your basis for which you want to know the coefficients, and the output of the network is the coefficient that you would have associated to that element of the basis in your ground state. And the idea is that in order to parameterize this mapping, you use a neural network, and in particular, a deep neural network. So what you do is you just consider that this is just a variational problem. You need to find a function. You know what are the properties of this function. They need to map every single state from your basis to the coefficient that the ground state wave function has. And in order to find what is the right parameterization, the only thing that you need to do is to just find the parameterization that minimizes the energy of your system. So the way one usually thinks about this is that when you want to find the ground state of a many-body Hamiltonian, you can think that you are dealing with a machine learning problem where the loss function is just simply the many-body energy. So if you find a parameterization that minimizes your loss function, which is the ground state energy, then you effectively found a parameterization of your ground state. So the trick with neural network quantum states is that in order to find both the, let's say, ground state energy and to minimize the ground and to obtain the ground state wave function, you can actually exploit the locality of Hamiltonians. So you can think that for a very specific expectation value, namely the Hamiltonian or the magnetization, you would like to compute it in this way. So an expectation value between the ground state, the specific operator ground state, then over the bracket of the ground state. And then you can do a little bit of algebra and actually decompose this term onto two different terms. One term that looks like a probability distribution, namely that is always positive and it's likely going to be peaked around some very specific part of your Hilbert space. And then another term in the Hamiltonian that is going to be, let's say, a set of coefficients, but what is most important is that thanks to the locality of your operators in the Hamiltonian is going to contain just a finite number of terms. So now what you need to do is actually to find the integral of a certain probability distribution times a very specific set of coefficients, which in particular is something that you can perform very efficiently using Monte Carlo sampling. So the deal with neural networks is that you use the neural network as a variation, many-body wave function, and then you actually compute all the observables, including ground state energy, magnetization, correlators, and so forth, using a Monte Carlo sampling over this very specific probability distribution. So, for example, if you think about the ground state energy, you would essentially say that the ground state energy can be decomposed on the expectation value of the different contributions to the ground state energy. That is what you call E local here. So this essentially stems from the locality of your Hamiltonian. And of course, the local contributions to the ground state energy are given by this expression over here. Now, to find the ground state wave function, you need to minimize with respect to the variational parameters of your neural network that here we represent as theta. So what you do is you minimize every single local contribution to the energy. In particular, you make the derivative of the total energy with respect to the parameter that essentially gives rise to this term over here. And now with this term, you can actually also compute it using your neural network concept, in particular using a Monte Carlo sampling with the expression that you have over here. So this essentially allows you to use backpropagation. So the idea is that you compute the derivative of the energy with respect to the parameter. This is a quantity that you can explicitly compute, and this allows you to update the different parameters of the Hamiltonian. So from a practical point of view, you essentially use, again, the variational principle. So you say that the ground state energy depends on the ground state wave function and the different parameters of the neural network. And this is going to be bigger or equal than the ground state energy. Now you minimize this quantity. You compute the ground state energy, you compute the gradient of the ground state energy with respect to the parameters. And then you redefine the parameters, let's say, using a very specific learning rate. So you compute with one very specific neural network, you compute the derivative, then you update the parameters, then you compute again the derivative, then you update again the parameters, and so forth, and so forth, and so forth. And this will eventually bring you to the ground state of the system. Now, in comparison with matrix product states, neural networks require this Monte Carlo sampling. In the case of matrix product states, you can actually do the minimization by, let's say, contracting the network exactly. So from a variational point of view, optimizing a matrix product state is actually easier than optimizing a neural network, because the neural network requires the Monte Carlo sampling. But what is important is that neural networks are actually not bounded by an area law. You can actually have states with a very large amount of entanglement parameterized by a neural network that would be nearly impossible to parameterize with a matrix product state or with a tensor network. And what is actually most important is that for neural network quantum states, we can actually leverage all the architecture and resources and methodology that have been developed for machine learning. And this, of course, allows you to, let's say, run neural networks in GPUs, to run them in parallel, and to use all the optimization and to reuse some of the optimization algorithms that we have in machine learning. And what is actually very important is that neural networks are actually a generalization of matrix product states and tensor networks. And in particular, there's a very specific type of neural network that is called the Boltzmann machine that is mathematically analogous to a matrix product state. So with this, I would like to finish. And if I could ask you to remember something, please remember that tensor networks are a very powerful methodology to deal with strongly interacting one-dimensional quantum many-body models, and that neural network quantum states provide a powerful methodology for two-dimensional models, and in particular that allows us to use techniques coming from machine learning to solve two-dimensional quantum many-body systems.